Gravity pulls things down. That is the most obvious statement in all of science. You drop a ball, it falls, you jump, you come back. The apple hits Newton on the head, and everybody says, "Ah, gravity," as if saying the word explains anything at all. I want to tell you something. That sentence, "gravity pulls things down," is not an explanation. It is a description. And the difference between a description and an explanation is the difference between watching a magic trick and knowing how the trick works. Most people never get past the trick. Somebody once asked me in an interview to explain how magnets work. Why do two magnets push each other away? And I refused to answer, not because I did not know, but because the question itself was sitting on a pile of assumptions so deep that if I tried to answer it the way the person wanted, I would be lying. I would be giving them the feeling of understanding without the understanding itself, and I do not like doing that. Now today I want to do something similar, but I want to go further. I want to talk about gravity. And I want to be honest about what we know, what we think we know, and what we absolutely do not know. Because the gap between those three things is enormous, and almost nobody talks about it. Let us start where you would expect. Let us start with Newton. Isaac Newton, sometime in the late 1600s, wrote down a law, and the law says this: every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. That is it. That is Newton's law of gravitation. You can write it in one line. The force equals g, a constant, times the first mass, times the second mass, divided by the distance squared. And this law is spectacularly good. You can use it to predict the motion of the planets. You can use it to figure out how much you weigh on the moon. You can use it to calculate the trajectory of a cannonball. Engineers use it. Astronomers use it. It works. So what is the problem? The problem is that Newton himself knew it was not an explanation. He said so. He wrote in the Principia words to the effect of, "I have described how gravity behaves, but I have not explained why it behaves that way." And he was bothered by this, deeply bothered. Think about what the law actually says. It says that the Earth right now is pulling on the moon, across 240,000 miles of empty space. Nothing in between. No rope, no chain, no beam of light carrying the message. Just a force, reaching across the void, grabbing the moon and pulling. Newton called this action at a distance, and he hated it. He said, and I am paraphrasing, that the idea that one body could act on another through a vacuum, with nothing mediating the interaction, was so absurd that no person with any competence in philosophy could accept it. And yet his equation worked. So people used it. They used it for 200 years. And gradually the discomfort faded. People stopped asking, how does it reach across space? And started saying, well, it just does, which is not an answer. That is surrender dressed up as confidence. Now I want you to notice something. The law tells you how strong the force is. It tells you which direction it points, but it tells you nothing, absolutely nothing about the mechanism. It is like saying, every time I clap my hands, a light turns on in the next room. That is a perfectly good description. You can predict when the light will turn on, but you have not explained anything until you find the wire. So for 2 centuries, physics had a description of gravity with no wire, no mechanism, just a formula that happened to match every observation. Then along comes Albert Einstein, 1915, and he does something outrageous. He says gravity is not a force. Let that land for a second. The thing you have been told your entire life is a force, the thing Newton wrote a force law about, the thing that keeps you stuck to this chair, Einstein says, is not a force at all. So what is it? Here is where it gets strange and beautiful, and honestly, a little unsettling. Einstein says that mass and energy warp the geometry of space and time, not metaphorically, literally. The Earth is not reaching out and grabbing you. The Earth is bending the fabric of space and time around itself, and you are moving through that bent fabric. What you feel as gravity, that pull toward the floor, is actually the geometry of the space you occupy, pushing you along a curved path. I know that sounds like mystical nonsense, so let me give you a way to see it. Imagine a rubber sheet stretched flat like a trampoline. Now put a bowling ball in the middle. The sheet sags. It curves inward around the bowling ball. Now roll a marble across the sheet. The marble does not travel in a straight line. It curves toward the bowling ball. Not because the bowling ball is reaching out with some invisible hand, but because the surface itself is curved. The marble is just following the surface. That is, in a very rough way, what Einstein is telling you. The Earth is the bowling ball. Space and time are the sheet, And you are the marble. You are not being pulled. You are following the only path available to you through curved spacetime. Now, this analogy is imperfect. The rubber sheet is two-dimensional. Real spacetime is four-dimensional, 3 of space and 1 of time. And the curvature is not just in space, it is in time. In fact, the warping of time is actually more important for everyday gravity than the warping of space. That part almost never gets mentioned, and it is one of the most beautiful aspects of the whole theory. Let me explain what I mean. You are sitting in a chair right now. Your head is slightly farther from the center of the earth than your feet. According to Einstein, time passes at a slightly different rate at your head than at your feet. Your head ages faster than your feet by an incredibly tiny amount. We are talking about fractions of a nanosecond over a lifetime. But it is real. It has been measured. Clocks at the top of a building tick faster than clocks in the basement. Now here is the key insight. Objects in free motion, objects that are not being pushed or pulled by anything, follow paths through spacetime that maximize their proper time. This is a technical statement, but what it means in plain English is that things naturally move toward where time runs slower, toward the center of mass, toward the earth. That tendency, that movement toward where time runs slower, is what you experience as gravity. So when you drop a ball, the ball is not being pulled by a force. The ball is following the straightest possible path through curved spacetime. In flat spacetime, that path would be a straight line. In curved spacetime, that path curves toward the earth. And the ball, from its own point of view, is not accelerating at all. It is in free fall. It is following the natural geometry of the universe. You, on the other hand, sitting in your chair, you are the one being accelerated. The chair is pushing you upward, preventing you from following your natural free fall path. That feeling of weight you have right now, that is not gravity pulling you down. That is the chair pushing you up. That is the electromagnetic force in the atoms of the chair resisting your natural motion through curved spacetime. I know. It is upside down from everything you were taught. But it is correct. And we know it is correct because the predictions Einstein made using this framework have been verified over and over and over again. Let me give you one that really drives it home. The global positioning system. Those satellites orbiting the Earth carry atomic clocks. And those clocks tick at a different rate than clocks on the ground. If the engineers did not correct for the relativistic time difference, the kind of time difference I just described, the GPS system would drift by about 10 kilometers per day. It would be useless in a few hours. They have to use Einstein's equations, not Newton's, to keep the system accurate. So Einstein's picture is better than Newton's. But is it an explanation? This is where I want to be very careful, because there is a temptation when you learn general relativity to say, now I understand gravity. Mass curves space-time, and objects follow the curves. Mystery solved. And I want to resist that, because you have to ask the next question. Why does mass curve space-time? Einstein's field equations tell you that mass and energy on one side equals space-time curvature on the other side. It is the most compact and elegant equation in all of physics, but it is still a description. It says that mass and curvature are related. It does not say why they are related. It does not explain the mechanism. We are back to the same problem Newton had. Newton said masses attract with a force proportional to their product and inversely proportional to the distance squared. Einstein said mass tells spacetime how to curve, and spacetime tells mass how to move. Both are beautiful descriptions. Neither is a complete explanation, and this is what I was getting at in that interview when the person asked me about magnets. When you ask why in physics, you are always standing on a platform of prior understanding. You ask why does the ball fall? I say because of gravity. You ask why does gravity exist? I say because mass curves spacetime. You ask why does mass curve spacetime? And now I am stuck. I can give you the equation. I can show you that it is consistent with every observation we have ever made, but I cannot tell you why the equation is what it is. At some point in every chain of why questions, you arrive at the boundary of what is known, and you have a choice. You can either pretend you understand and give a comfortable but dishonest answer, or you can say, this is where our understanding stops. This is the edge. I prefer the edge. I think the edge is the most exciting place in all of science. Let me take you to that edge now. Because when you stand there and look out at what we do not know about gravity, the view is spectacular. Here is the first thing we do not know. General relativity, Einstein's theory, is a classical theory. It describes space-time as a smooth, continuous fabric. But we know from quantum mechanics that nature is not smooth and continuous at very small scales. At the quantum level, everything is granular, probabilistic, and deeply strange. Every other force in nature has been successfully described using quantum mechanics. The electromagnetic force, the force that holds atoms together, the force that makes light, that has a quantum theory. We call it quantum electrodynamics. The strong nuclear force, the force that holds the nucleus together, that has a quantum theory, quantum chromodynamics. The weak nuclear force, the one responsible for certain kinds of radioactive decay, that has a quantum theory too. Gravity does not. We do not have a quantum theory of gravity, and it is not for lack of trying. Some of the most brilliant people on the planet have been working on this problem for decades, and we are still stuck. The problem is not just technical, it is conceptual. In quantum mechanics, things happen in a fixed background of space and time. You put your particles in space-time, and you calculate what they do. But in general relativity, space-time itself is the thing that is dynamic. Space-time is not the stage. Space-time is one of the actors. So when you try to apply quantum rules to gravity, you are trying to apply rules that assume a fixed stage to a performer that is the stage. The whole framework breaks down. What happens at the very center of a black hole, where general relativity predicts that space-time curvature becomes infinite? We do not know. Our theory produces infinity, and infinity in a physics calculation is usually a sign that you have pushed the theory beyond where it is valid. Something else is happening there, something quantum, and we do not yet have the language to describe it. What happened at the very first instant of the universe, at the Big Bang, when all the matter and energy in the cosmos was compressed to a point of infinite density? Again, we do not know. General relativity breaks down right where we need it most. Now let me take this in a direction that might surprise you. There is another way to think about gravity that is very different from both Newton and Einstein, and it starts with a question that sounds almost childish. Why do things fall at the same rate? Galileo showed this. Drop a hammer and a feather in a vacuum, and they hit the ground at the same time. It does not matter what the object is made of. It does not matter how heavy it is. Everything falls at the same rate. In Newton's framework, this is a coincidence, a miraculous coincidence, because Newton says the gravitational force on an object depends on its mass. A heavier object feels a stronger pull. But Newton also says that the resistance to acceleration, what we call inertia, depends on the same mass. So a heavier object is harder to accelerate. And these two effects, the stronger pull and the greater resistance, cancel out perfectly, every time, for every object, without exception. But why should the mass that governs gravitational attraction be the same as the mass that governs inertia? These are in principle completely different properties. One is about how much gravity you feel. The other is about how hard you are to push. There is no obvious reason they should be equal, and yet they are, to extraordinary precision. Experiments have verified this equivalence to better than 1 part in 10 trillion. Einstein took this coincidence and said, what if it is not a coincidence? What if the reason gravitational mass equals inertial mass is that gravity and acceleration are literally the same thing? This is the equivalence principle, and it is the conceptual foundation of all of general relativity. Here is what it means. Imagine you are in a closed box with no windows. The box is sitting on the surface of the earth. You feel your weight. You feel pulled toward the floor. Now imagine a different situation. The box is in deep space, far from any planet or star, but a rocket engine underneath is accelerating the box upward at exactly the right rate. You would feel exactly the same pull toward the floor, exactly the same weight. Every experiment you could do inside that box would give the same result in both cases. Einstein said these two situations are not just similar, they are identical. There is no experiment you can do in principle to tell the difference between being in a gravitational field and being in an accelerating reference frame. Gravity and acceleration are the same phenomenon. And from this one insight, this one deceptively simple idea, the entire structure of general relativity follows. The curvature of spacetime, the bending of light around massive objects, the slowing of time near heavy bodies, the existence of gravitational waves, black holes, the expansion of the universe, all of it follows from the equivalence principle. That is the power of a deep insight. It does not just explain one thing, it reorganizes everything. But even here, even with this beautiful and powerful framework, we are still left with the question why. Why is the equivalence principle true? Why should gravity and acceleration be the same? Einstein did not answer that. He took it as a starting axiom and built the most successful theory of gravity ever constructed. But the axiom itself remains unexplained. Now I want to take you somewhere else entirely. Because gravity does something that no other force does. And this property might be the deepest clue we have. Gravity is universal. It acts on everything, every particle, every form of energy, every quantum of light. You cannot shield yourself from gravity. You cannot build a gravitational insulator. There is no material in the universe that is neutral to gravity, the way a neutral atom is neutral to electricity. Everything responds to gravity. Everything contributes to gravity. This is unique. The electromagnetic force acts on charged particles, but not on neutral ones. The strong force acts on quarks and gluons, but not on electrons. The weak force is selective in its own ways. But gravity is democratic. It plays no favorites. It couples to the total energy content of the universe, period. This universality is what makes gravity so different from the other forces. And it might be the reason we have such a hard time making a quantum theory of it. Because the other forces operate within spacetime on specific types of particles. Gravity operates on spacetime itself. It is not one of the players in the game. It is the game board. Some physicists have suggested that maybe gravity is not a force at all, even in a generalized sense. Maybe it is not something that needs to be quantized. Maybe gravity is an emergent phenomenon, something that arises from the collective behavior of more fundamental degrees of freedom, the way temperature arises from the collective motion of atoms. You do not quantize temperature. You do not look for the temperature particle. Temperature is a statistical property, a macroscopic concept that emerges when you have a huge number of microscopic things doing their business. Some very serious people think gravity might be similar. That space-time itself might be made of something, some underlying quantum structure, and what we call gravity is the large-scale behavior of that structure. If that is true, then trying to quantize gravity is like trying to quantize temperature. You are looking for a fundamental theory of the wrong thing. The fundamental theory is not about gravity. It is about whatever gravity is made of. This is speculative. I want to be clear about that. We do not have a confirmed theory along these lines. But it is one of the live ideas, and it shows you how deep the rabbit hole goes. Let me give you another piece of the puzzle that keeps physicists awake at night. The cosmological constant problem. When you try to calculate the energy of empty space using quantum field theory, you get a number. And when you compare that number to the observed effect of dark energy, the thing that is accelerating the expansion of the universe, the two numbers disagree by a factor of about 10 to the power of 120. 10 to the 120. That is not a small disagreement. That is arguably the worst prediction in the entire history of physics. The discrepancy is so enormous, so absurd, that it suggests we are fundamentally misunderstanding something about how gravity and quantum mechanics interact at the level of the vacuum itself, and nobody knows how to fix it. Truly, this is not a case where we have three competing solutions and we need an experiment to decide between them. We have no good solution. The cosmological constant problem is one of the deepest unsolved problems in all of physics. So let me come back to the original question. What is gravity? Here is my honest answer. Gravity is a phenomenon we can describe with extraordinary precision. We can predict the orbit of Mercury to astonishing accuracy. We can detect gravitational waves from black holes merging 1 billion light-years away. We can measure the bending of starlight around the sun. We can calculate the expansion rate of the universe. But we cannot tell you what it is in the deepest sense. We know how it behaves. We know the mathematical structure that governs it. We know that it is intimately connected to the geometry of space and time. And we know that our current understanding breaks down at the smallest scales and the most extreme conditions. This is not a failure of physics. This is the frontier. I find this exhilarating. Because we are not talking about minor details. We are not arguing over the 7th decimal place. We are talking about one of the 4 fundamental forces of nature, something you feel every second of your life, and at the deepest level we do not understand it. When that interviewer asked me to explain how magnets work, what I was really trying to say was this. The depth of a why question is limitless. You can always ask one more why, and at each level you might discover that the thing you thought you understood was resting on something you had never even considered. Gravity is the perfect example. You start by saying things fall, you progress to Newton, who says there is a force. You progress to Einstein, who says there is no force, only geometry. And then you ask why geometry, and you are standing at the edge of human knowledge, looking into a void as deep as the one Newton worried about 300 years ago. The honest answer, the Feynman answer, if you want to call it that, is this. We do not know what gravity is. We know what it does. We know the rules it follows. We can predict its effects better than almost anything else in nature. But the deep question, the why does it exist question, the why these rules and not other rules question, remains open. And that openness is not an embarrassment. It is an invitation, because somewhere, possibly in this room, possibly in a classroom on the other side of the world, there is someone who is going to figure out the next piece, someone who is going to ask a question nobody thought to ask, or notice a pattern nobody thought to look for, and push the boundary a little further. I hope that person knows something. I hope they know that it is perfectly fine, in fact it is necessary, to sit with not knowing. The discomfort of not understanding is not a sign of failure. It is the sign that you are in the right place, you are at the edge. And the edge is where all the interesting things happen. I want you to think about this. Tonight, when you are lying in bed, you are being held against the mattress by a phenomenon that has shaped the formation of every star, every galaxy, every planet in the observable universe. A phenomenon that Einstein reimagined as the curvature of time itself. A phenomenon that breaks our most fundamental theories at the smallest scales, and you feel it as nothing more than the comfortable weight of a blanket. That should keep you up for a while. Tell me, what do you think gravity is? Not the textbook answer. Your answer.